Thank you, Sumitra. To continue and discuss further about kernels, I need to address an issue about convergence. When we have, say, a Hilbert space, I mean, it is the same if we are in a Banach space, and a collection of families, of family of function HS, where our parameter S is not necessarily a countable set. What do you mean by H equal sum HS S in our set S? Understanding the meaning of this is important, even if S is countable. It's a type of convergence which is called unconditional convergence. And even before giving the definition, to highlight in the countable setting, it's important to understand the meaning and consider these examples. Even for scalars, sum of -1 to the power n over n, n from 1 to infinity. This is something that we study in analysis, calculus or analysis 1. And I've been using methods like Leibniz method. We can show that it is, convergent. And you can obtain an estimation for its value. Based on the definition I want to give today, and sum n from 1 to infinity is not the right notation. I should write sum n to n, where n is the natural number, -1 to the n, where n is not convergent. True. And you may say that, oh, it's true because it's not absolutely convergent, but it's more than that. It's more than that. Unconditional convergence is even stronger than absolute convergence. I can, when it's clear for you, I can give you examples of even sequences which are absolutely convergent, but not unconditionally convergent. It's a very important topic in Banach space theory. We saw a version of this when we studied positive quantities. HS here was a positive real number, and I gave a meaning to this back to 3 weeks ago. But now HS is a function in a Hilbert space, or even in an abstract setting, an element of a Banach space. Here is the definition. Again, a type of epsilon delta definition, which people do not like, but it's the key. And when you get used to this, you see that that's really the key point. And arriving at this definition has not been easy for the mathematician. It took many, many versions until they arrive at this format. So we say that F is equal to the sum of Fs, S in some index space S if, did I use F or H above? I use H, F, doesn't matter. If for every epsilon, there is a finite set F0 in S, a finite set of indices such that for any finite set S, which is bigger than, sorry, F, which is bigger than F0. F0 is in F, is in S. For any finite set bigger than this F0, of course, F0 depends on epsilon, but after that, the norm of F minus sum Fs, S is in F. Not that there is no ambiguity about this sum because it's a finite number of elements in our space is less than epsilon. So for any finite set, for every epsilon, there is a finite set F0, F0 or epsilon, such that, say, after that, if you add any other finite number of elements, the difference is not that big, it stays less than epsilon. If this is the case, we say that the sum of S is unconditionally equal to F. In the case these quantities are positive, somehow we return to the classical setting, because if Fs, they are positive numbers, belongs to R plus, and sum of Fs is finite, the way I defined above, then we can conclude that the set of S such that Fs is not equal to 0 is countable. Yeah, we can index them as S1, S2, S3, so on. On the complement of this, Fs is identically equal to 0, and set of S such that the sum of Fs is actually the sum of Fsi, the one we know from our studies of series. It's the same as before. And here the ordering is not important because everything is positive. That's for the positive, but if not positive, we need to be careful. Many strange things may happen. The best way to treat unconditional convergence is to stick to this definition.
So this is just the convergence in terms of nets.
Yes. Yeah, it's a definition. I mean, the way I didn't mention the name net, but if you consider the family of
Finite set with the inclusion,
it's a net, and this is the same as, again, I mean, I mentioned the name of Moore. This is the same as limit of this sum is equal to F, but limit not as a sequence, as a net. True?
and
If
yeah,
I come back here, the way I define is equivalent to this. Sum of Fs, S belongs to a finite set F. Call this, say, X, which depends on F. X index F is well defined because F is finite. And now, if you find the lim over F of XF, the way more defined for nets. This is precisely what I defined for unconditional convergence. It's the same thing. With, I mean, I use a different language, but it's the same things. It was the first talk today. We talk about Parseval identities. So if you are in a Hilbert space H with ES, S in S, and orthonormal basis, orthonormal basis, not necessarily a separable space. So S here is not a countable set, but for any H in the space H, Parseval identity says that the norm of H squared is equal to absolute value H inner product with ES in the space H squared, S in S. And for this, because everything is positive, we know that despite the fact that the sum could be a huge sum, huge in terms of a number of elements which are in it, and that number is not necessarily countable, but still, in this case, we can say a countable number of them is not zero, and we can transform this sum into a regular sum that we have seen before. So there's less than J here, but there is another version that is also called Parseval identity of this, at least two more versions. The first one is to use the polarization identity and conclude that for every, say, F and G, the inner product of F and G in H is equal to the sum S in S, F inner product with ES, G inner product with ES bar, and gain everything in H. It becomes a bit more sensitive here because the numbers here are no longer positive ones. These are complex numbers. So going from here to there, even though it's straightforward, but care is needed. And now we have to use the definition I mentioned because of not having a positive number. And the third one, which is still even more, way more care is needed, is to say that for any F or for any H, we can write H as this identity. So note that here we are in R plus, here we are in C, and here we are in H. In R plus, we can go back to the standard or previous definition. In C, and in particular in H, we need the new definition. The third one in H in particular means that the sum on the right side is unconditionally convergent to H. The meaning of this was given above. A conclusion of this is the following theorem. Well, let H be an RKHS on omega with kernel K. Then the way suppose that ES S on an index set S is an orthonormal basis for H. Then gives a formula for capital K. Capital K at the point XY is given by some S in S, ES at point X, ES at point Y bar. And well, the convergence is at each point, and we know the meaning of this convergence now. And indeed, when we look at the proof is a consequence of this identity in H, which by itself is important, but it's not mentioned as a part of the proof, a part of the theorem. I think it's important to include it as a result. That's why I say then this and ky is equal to the sum S in S ESY bar ES. For this is a convergence in C, but this is a convergence in H. Both unconditional convergence the way we defined it above. And indeed, I proved the second one first and used the second one to obtain the first one. Proof based on the explanation above is very easy. For every, we saw that for every H in H, indeed, H is equal to the sum S in S. That's the meaning of having an orthonormal basis. We have this since ES is an orthonormal basis. It's a consequence of, I mean, it's hidden in the definition of basis, and even we can say that this is one of the partial identities. So now replace H by KY. We put H equal to KY. So KY is equal to sum S in S, KY ES ES, which easily seem to be ES inner product with KY bar ES, and any function inner product with KY is the value of this function at point Y. So the sum is in S. This function evaluated at point Y, and there is a bar ES, and the convergence is unconditional convergence is in H. We know that when we have convergence in H, it implies pointwise convergence. This is one of the easy result that we saw, before the break. In terms of the sequences, but it also works for this setting. So this immediately, the fact that ky is equal to the sum ESY bar ES immediately implies that for every x, ky at point x is also equal to the coefficient and this function evaluated at point x. And this is what we wanted to prove. That's the end of proof. And then it's added in the book that we can use this formula. This is equal to k of xy. We can use this formula to obtain kernel. In the examples we saw before, in 4 examples of Sobolev spaces and then some analytic functional spaces, and even in the Pauli-Wiener space, in some of them we already know an orthonormal basis. For example, in H2, it's separable. Instead of ES, I write En of Z equal to Zn, n bigger than or equal to 0. We know that En bigger than 0 is an orthonormal basis for H2. Even though we found already the kernel, but that's another way to do it. Based on the previous result, so we can conclude that k at point ZW, instead of x and y, I use x and w, are a complex number, is the sum, get the right n in n, En at the point Z, En at point W bar. So the sum n is in n, Z and W in bar. So ZW bar power n. Up to here is the sum, the way I defined about the unconditional convergence that we saw. But ZW bar in absolute value is less than 1. And this sum is equal to the sum we had before, the traditional one. Just because of this, it's unconditionally and even absolutely convergence. I mentioned both because these are not the same. In this context, they coincide. It's absolutely convergent, is unconditionally convergent. So these two notions coincide. And instead of sum n is in n, I can write sum n from 0 to infinity, which is equal to 1 over 1 minus ZW, or we saw this and call it Cauchy-Jacob kernel. Cauchy-Jacob kernel. Just let me modify one thing. And I think here, instead of n, I better to write n not, because n is usually 1 to 3, not included 0. But when we write n not, 0 is just matter of notation. So this is a good way to find the the kernel for the Hardy space. There is an attempt in the book, which, I mean, I do not agree with that, but I explain what it says, to find the kernel of the first space we studied. It was this one, H, function f from 0, 1 to r, such that f is absolutely continuous, f prime is in L2, and boundary condition equal to 1. We found the kernel by using distribution theory. Sheldon provided a PDF file explaining how to use a very neat elementary method to find it. And here is another method which eventually gives a formula, but I mean, it's a kind of delicate at the end. We'll see why. But the first step is to find an orthonormal basis if we want to use the formula above. So what is an orthonormal basis for H? Remember, the inner product F and G in H is integral from 0 to 1, F prime X, G prime X. I mean, we don't need bar here, everything is real, but in complex setting, you should put a bar there too. In L2, either L2 of t or L2 of 0 to pi, so some preparation. L2 of t or L2 of 0 to pi, we know the basis. It's e to the I n theta. N in Z. And if we want to consider the real case, these are for the complex case, by using Euler formula, e to the I theta is cos theta plus I sine theta, we see that this is constant 1, then sine n theta and cosine n theta, n bigger than or equal to 1. I didn't put 0 because the normalizing coefficients are different. These are orthogonal, but not normal. If you want to normalize, you have to add some coefficients here. I mean, alpha 0 here, alpha, alpha n here, beta n here. You can find alpha n, beta n such that this is orthonormal. But the important thing here is the combination n theta with cosine, sine, and the coefficient. If we change the scale, which I need here, and consider L2 of 0, 1, then my basis is still, the constant remains constant, but sine becomes 2 pi n theta, because I mean, I replace 0 to pi by 0, 1 is a change of scale, and cosine n 2 pi n theta, n bigger than 1. This is orthogonal, and if you want to normalize again, I mean, you put, it's not the same as above, it's different, but still, I mean, we can call it alpha n, beta n to obtain an orthonormal basis. Now, if we start with elements in this space, the original one, Fn, then Fn and Gn, for the inner product, it's integral of Fn prime, Gn prime. So our Fn at Gn should be such that the prime is equal to this, to have something orthogonal and then normalized to be orthogonal. So I should look for the solution of y prime equal to 1. y prime equal to sine 2 pi n theta, and y prime equal to cosine 2 pi n theta to obtain elements in the space, the original space, which are orthogonal together. The solution of this is a constant here. The solution of this one is 1 over 2 pi n. Well, cos 2 pi n theta with a minus plus another constant here. And with the other one is y equal to 1 over 2 pi n sine 2 pi n theta plus c. The constants are not necessarily the same. I just wrote c all the time. And remember, that's the solution of the equation. At the same time, I want to have y of 1 equal to y of 0 equal to 0. We have some boundary values. So this kills the first opportunity, no constant. The constant should be identically 0. And then we can find the constant here and the constant there such that these are satisfied. It's very easy, just plug in. And you see that the solutions are here. I mean, I look at the book and copy paste. The first solution is cosine 2 p n theta minus 1. That's the function which is orthogonal to the function just sine 2 p n theta. And if you want to normalize it, the factor is 1 over root 2 pi n, and here 1 over root 2 pi n. And the authors call this CNT, and this is SNT. That's very good. So we obtain n bigger than or equal to 1. So these are in space H, and they form an orthonormal sequence. This is now very easy to prove, because when you take the derivative of this one, you immediately obtain what we had before. And in interval 0, 1, these are sequences which are orthogonal. Coefficient in front are adjusted such that the norm is equal to 1, so it's normalized too. And why is it complete? I used this technique before. Just start with the assumption f being orthogonal to Cn and being orthogonal to Sn, and do a little bit of calculation, very straightforward to deduce that f is identically 0. So it's more than being an orthonormal sequence. Indeed, it's an orthonormal basis. So that's good up to here. I obtain an orthonormal basis for my space H. I didn't know when I studied this space, I didn't find this orthonormal basis. But knowing this, now we can say that therefore K at point X and Y is equal to the sum let me call it En for the time being. En at point X, En at point Y. Bar is not needed because everything is real. And the summation is over n. And we have two types of En here, either Cn or Sn. So it's sum n from 1 to infinity, Cnx, Cny plus Snx, Sny. And I know that the convergence is good, and I can plug and do the summation. And if you look at the page 20 of the book, I mean, after some calculation, there is a typo which is not important, but after some calculations, they obtain the summation over n cosine 2 pi n x minus y minus cosine 2 pi n x minus cosine 2 pi ny plus 1 divided by 2 pi squared n squared. Up to here, there's absolutely no problem. I mean we have series of complex numbers, the real numbers, they behave well. And then I do not see, absolutely do not see how from here we can conclude this is equal to 1 minus y x if x is less than or equal to y, and y times 1 minus x if x is bigger than or equal to y. This is the way written on page 20. And as I said, there is no mathematical error in this. Even up to this point, everything is straightforward. Just going from this step to this is the part I do not see. Of course, backward, it's easy, because if this function is given, I mean, if this is given, this function, if this is given, and they ask, find the Fourier series of this, going from here to there is straightforward, because you have explicit formula for the Fourier series. But the other way around, I mean, coming from the Fourier series to the function, I do not know how to do it. If you have a remedy, shortcut to do this, please let me know. Well, I think it finishes our course today. If there is no question, I have a comment to make about next week. Is there any question? You may stop sharing, Sumitra, please.